Hi, everyone. I hope this is going to work. I really have no idea what I'm doing, but we're going to give this a try. So I'm going to be taking notes from my iPad, and hopefully it'll show up on my screen here. I'm trying to be on the cutting edge of technology here, but we'll see. So sound waves. Today we're going to talk about sound waves. Sound comes from the vibration of particles. So sound comes from the vibration of particles. So sound is three types of wave, technically. Sound is a mechanical wave, meaning what that means is it cannot travel in a vacuum. It needs a medium to vibrate off. Okay, so sound cannot travel in space. I think I've told you this already, but if sound could travel in space, the sound that the sun makes would be louder than being 5 feet away from a chainsaw. So that would be really annoying. Light, of course, can travel in space, but sound cannot. We know that light can travel in space because we can see the sun and we can see other things. If we had no sun, we wouldn't be able to see much. Sound is also a longitudinal wave. And we know from last chapter that that means that the amplitude changes are parallel to the motion of the wave. Okay. And then the next thing we are going, hold on. The next thing we're going to talk about, or the next type of wave that sound is a pressure wave. And what that means is we have areas of high and low pressure called compressions and rarefactions. Okay. When we have sound, we have we have we need, as we said, it's a mechanical wave. When we have sound, we need a medium for that sound to travel through. The means by which that sound will travel, the material by which the sound travels. Okay. So the medium is the material through which the wave travels. Okay. For sound, the medium can be solid, liquid, or gas. Okay. You drop an aluminum pan on the ground, it starts to vibrate, it creates sound. Liquid, if I went underwater and I screamed, you would be able to hear me. It'd be muffled, but you would be able to hear me. And then gas, air is a gas. Sound can travel through gases. helium. Sound can travel through helium, right? So a longitudinal wave is so you're going to have compressions and rarefactions in this longitudinal wave. The compressions are the areas of high pressure, and the rarefactions are the areas of low pressure. So shouldn't be touching my eye. What you see here, so this is a tuning fork. That is not a football goalpost. That is a tuning fork. So if the tuning fork vibrates, see my cute little vibrating lines. What you're going to see here is you are going to see an area of low pressure where there's not that many air particles, and then an area of high pressure where there's a bunch of air particles. And then, another area of low pressure, not too many air particles, and then another area of high pressure where there's a bunch of air particles. Okay, so the rarefactions are here and here, okay, and the compressions are here and here where there's high pressure. Okay. I totally forgot that I can change colors. That's so exciting. All right. A sound wave is a disturbance that travels through a medium. As one particle is disturbed, it exerts a force on the adjacent particle, and that is how the energy is carried. So what you can think of it, let's pretend you had a bunch of air hockey pucks on an air hockey table, okay? As let's say you have a bunch of pucks here. Now, one puck hits this puck's going to hit this puck, and that's going to move, okay? And it also might hit this puck, and this puck hits this puck, okay? And so what you're going to be left here is an area of low pressure here and high pressure over here, because all of the pucks will move that way, okay? And so that's where the compression and the rarefaction comes from. The human ear is capable of detecting sounds between 20 hertz and 20,000 hertz, okay? Sounds at the frequency below that range, those are called infrasonic. And anything above 20,000 is going to be ultrasonic, okay? And so these are just some examples of animals' hearing ranges. I think it's pretty nuts that dolphins can get up to 200,000 hertz. That's 10 times our audible range, or our audible maximum. So if you ever hear, if you go to YouTube and you hear like dolphin or whale sounds, like they're super high pitched, okay? And that's pitch is related to frequency, okay? Pitch is the perception of frequency. Okay, so the higher the frequency, the higher the pitch. Ready? High frequency noise. Ah! Okay. Low frequency noise. Oh, I just did that. So, whenever you have a high-pitched noise, we're talking about a high frequency. Whenever you have a low-pitched noise, That's a low frequency. So speed of sound wave, that's just the distance that the sound wave covers. So how fast it's moving. How fast the sound wave is moving. Okay. And oops. So I should really turn my notifications off, but it's fine. And so do not confuse frequency with speed. Okay, speed is how fast, and frequency is how many waves there are. Okay, so frequency, if we remember, frequency is the number of disturbances over the time, whereas speed is equal to either velocity is distance over time, speed is distance over time, or frequency times wavelength, right? So if a sound wave were observed to travel a distance of 700 meters in 2 seconds, then the speed of the wave would be what? So that's if the distance is 700 meters and the time is 2 seconds, then we can say V equals D over T. That's easy. 700 meters over 2 seconds, that's going to be 350 meters per second, okay? So sometimes you'll be asked to solve for D over T. Sometimes you'll be asked to do F times lambda. So don't be confused, because lambda is, that's a length, that's a distance, but it's a wavelength, right? And distance is how far the wave actually travels. Okay, so those are two different things. You gotta be careful with that. Okay, so the speed of a sound also depends on the temperature of a gas and the masses of the particles in the gas. Okay, the higher the mass, the higher the density. Okay, so actually, that's sort of a bad way to think about it. We'll talk about that in a second. So if we have higher temperature, that means the particles are going to be moving faster. So if the particles are moving faster, then they're going to be able to bump into each other more. Oh my God, what just happened? They're going to be able to bump into each other more. Okay, and then if they are lighter particles move faster. As well, so it's the same idea. For example, so if you have in helium, if you talk into helium, V equals F times lambda, right? Everybody knows what happens if you inhale helium and then you try and talk. You sound like this. So so the speed is increased. The reason for that is the speed is increased, the wavelength stays the same, and that causes the frequency to increase. And if the frequencies increase, what's increased? We talked about that earlier. When we have a higher frequency, we have a higher pitch, and that's why when you speak into, when you inhale helium, it sounds really high pitched. Okay, so elasticity, the speed of the sound is affected by a material's elasticity. Elasticity is the ability of a material to change shape and return to its original shape. Okay. In elastic materials, the atoms are close together and respond quickly to each other's motions. Okay. Steel is very elastic. And putty is very inelastic. Sound intensity. Okay. Sound intensity is how large the amplitude of a sound wave is. Okay. So loudness is the sensation of sound intensity. So a sound wave with a higher amplitude is carrying more energy, is louder. Okay. The natural frequency is when any object of an elastic material is disturbed, it vibrates at specific frequencies. So, for example, if you have a tuning fork, okay, tuning forks have different frequencies that they're associated with. So, if I hit a tuning fork that is 343 hertz, it's going to vibrate at 343 hertz. If I hit a tuning fork that's 256 hertz, it's going to vibrate at 256 hertz. Those are the natural frequencies of those tuning forks. Okay. So those are, and other objects have, if they are hit, if they are struck, then they are going to vibrate at very certain frequencies. Okay. So some objects have like one frequency that they vibrate at, and some objects have a whole set of frequencies that they can vibrate at. Okay. So, if the amplitude of these vibrations is large enough, and if the natural frequency is within the human hearing range, then the vibrating objects will produce audible sound waves. Okay, so some objects tend to vibrate at a single frequency, as I said, and they are often said to produce a pure tone. Okay, other objects like flutes produce pure tones, very specific frequencies depending on which hole that you're holding. I don't know. And other objects produce like have many different natural frequencies. So when you strike them, they're going to produce all sorts of different frequencies all at once. Those are said to produce a rich sound. Okay, a tuba sort of vibrates at all different types of frequencies. If I dropped a aluminum pan, actually, I have a cookie sheet right here. I'm gonna drop my cookie sheet on the ground. Everybody, listen. Hi. So that sort of produces all different types of sounds. Okay. All right. A force vibration is when an object, when adjacent objects, oops, cause other objects to vibrate. Okay. And resonance is when um, when objects vibrating at the same frequency produce um, a larger sound. Okay. The result of resonance is always a louder sound. A larger vibration, we can say. Larger vibration, so louder sound. And what that is resonance is the result of constructive interference. Okay, constructive interference. Two sound waves are in phase and they create a louder sound. Destructive interference, softer sound or no sound at all. So here's what you have to do. You print these notes out. Print out the document that I posted online, and then copy down all of these notes. Take a picture of them, send it to me. That's how I know that you did the notes. I would rather you not do this online because then you guys can share stuff with each other, and I don't know that you guys have gone through the actual notes. I really want to make sure you guys are actually doing this and learning. So have a wonderful rest of your day. Be good to each other. Okay.